So when we quantify these reactions, we give a quantity to them, we have to talk about the mole ratio. Okay, and a mole ratio is a conversion factor that allows us to basically compare any two substances in a chemical reaction. Okay, so that relates the amounts, or you can say allows us to compare, if that wording sounds better to you. It gives us the ability to compare two different substances in chemical reactions. So in the review of conversions that we did last class, from converting from grams to moles or grams to molecules, we stayed with one compound, right? If we started with sodium nitrate, we ended with sodium nitrate. Now we're going to be able to compare the reactants of a chemical reaction to one of the products. Okay, we're going to be able to switch between compounds within a conversion or within a calculation, and the mole ratio step is how we do that. Okay, so when we compare these mole ratios, you can put this down, or you can just listen as we walk through it. That's totally up to you. We have a reaction. First of all, is it balanced? Let's check to make sure this equation is balanced. Right, how many potassiums here? 2 and 2. How many chlorines? 2 and 2. And how many oxygens? 6 and 6. So we're good on the balancing part. Tell me what type of a reaction this is. Good, decomposition. We start with a complex molecule. We break it down into two or more simpler molecules. Very good. Okay, so it's a decomposition. Let's look at what is the mole ratio between potassium chlorate and oxygen gas. What's the mole ratio here between these two things? Okay, what do these coefficients in front of our compound tell us? How many single molecules are in this reaction? Or you remember we talked about we can scale it up to a molar quantity. So this tells us that 2 moles of potassium chlorate reacting with 2 moles of potassium chlorate can decompose into 2 moles of potassium chloride and 3 moles of oxygen. Okay? So when we talk about the mole ratio here between these two things, our mole ratio would be 2 to 3. Right? 2 moles of KClO3 to 3 moles of O2. Okay, does that make sense where we're looking at that? We're just looking at the coefficients right in front here. Okay, so if I asked you for the mole ratio now between potassium chlorate and potassium chloride, what would it be? 2 to 2, right? And if it's the same, you can reduce it, but 2 to 2 is fine. Okay? All right. So all that's telling us is that in this reaction, it takes 2 moles of potassium chlorate to make 3 moles of oxygen. Okay? Or a ratio that's similar to that, right? You're going to end up with 33% more oxygen in terms of its molar quantity than you started with in potassium chlorate. Okay, the ratio is what's important. So let's go ahead and balance this reaction. Okay, we're going to go ahead and balance the reaction, and then we're going to talk about mole ratios. So do we have a balanced reaction here? What should our coefficients be? Good, 1, 2, 1, 2. Okay, we needed 2 nitrates, so we had to add a 2 here, which means we need 2 silvers as well. Okay, so 1, 2, 1, 2. What's the mole ratio here between copper and silver? 1 to 2, right? So we would say it takes 1 mole of copper plus this to produce 2 moles of silver. Okay, do we see the ratios that go into that? We might not even start with 1 full mole of copper. We could start with 10 grams, right? But the ratio of our product would match the mole ratio. Okay, and we're going to look at that here. So now we're going to take the mole ratio a step farther. Okay, right? The mole ratio step is the only place you can compare 2 molecules. That's really important here. But now we're going to look at if we start in moles, right? If I say we had 6 moles of copper, how many moles of silver can we produce? We're going to look at how we can predict that reaction, okay? So we're going to take the amount of given substance and convert it to the amount of unknown substance in moles, okay? This is the easiest type of problem or conversion that we'll do in stoichiometry, so we're starting with the basics and then we'll build out. I'd go ahead and put this reaction down. I'll try to go ahead and balance it for you. That should be balanced, right? Here's our balanced equation. We want to know how many moles of lithium hydroxide are required to react with 20 moles of carbon dioxide. Okay, so in order to form these products, we want to see what would be required of lithium hydroxide in order to complete this reaction, right? If we start with 20 moles of CO2, how many moles of lithium hydroxide do we need to complete this reaction? Okay, so the T-chart works the same way. This is going to be a lot of T-charts, a lot of conversions that way. Okay, so what is the first step in a T-chart always? Right, what we know, right? And we know 20 moles of CO2. Okay? And our overall goal here is to find moles of lithium hydroxide. Okay? But how can we convert between carbon dioxide and lithium hydroxide? What's the one place we can do that? Yeah, it has to be in moles, right? That's our mole ratio step. So the only place that we can have 2 different substances in one column in our T-chart has to be a mole ratio step. So it's got to be moles to moles, okay? So if I want to get rid of moles of carbon dioxide, and I want to go 2 moles of lithium hydroxide, this would be our mole ratio step right here, right? Because I have 2 different substances in the same column. The only time that can happen is when it is moles to moles. Okay? This is also a step in our periodic table, the step in our T-chart in which the moles doesn't necessarily get the 1, right? If we're going moles to grams or moles to molecules, we know moles gets the 1. In this step right here, the mole ratio step, we look at the coefficients from the problem. Okay, just like we asked a little bit ago, what's the mole ratio between copper and silver? We're doing the same thing. So in this step, we look at the coefficients directly in the equation. So what should go right here? A 2. And what should go here? A 1. Okay, so that's our mole ratio right there. I know this seems kind of simplistic right now, but it will get more complex. Okay, so hopefully this was kind of a little common sense for us, right? If we started with 1 mole and we started with 2 moles, right? If we make this 20, that should automatically make this 40. Okay, but I want you to see the process that goes into it. Questions here? So in order to have a reaction with 20 moles of carbon dioxide, we had to have 40 moles of lithium hydroxide. Otherwise, the reaction wouldn't have gone all the way to its completion, and it would have stopped early. Okay? Does that part make sense? Okay. Okay, we already did all this, blah, blah, blah. Okay. All right. Okay, I went ahead and balanced it for you. So it's 2H2O2 yields 2H2O plus oxygen. Okay, does anyone know what H2O2 is? Yeah, hydrogen peroxide. And the stuff you put on cuts and scrapes. Okay, and what type of reaction is this? Decomposition, good. Okay. How many moles of oxygen gas will result from the decomposition of 5 moles of hydrogen peroxide? Okay, so in our T-chart here, remember it's pretty simple. We start with 5 moles of H2O2. Okay, then what is this step of our T-chart going to be? What do we call it? The mole ratio step. Good, the mole ratio step. I want you to understand this step's not always going to go second, right? So don't try to think about, oh, this step goes first, this step goes second. You have to read what your teacher is telling you. Okay, so I want to get rid of moles of hydrogen peroxide, and I want to go 2 moles of oxygen. Okay, so here, what would our mole ratio be from top to bottom? 1 to 2. Good. And the only way I'm getting these numbers are the coefficients here from our balanced reaction. So we need to understand if we balance our reaction incorrectly, it's going to throw off our mole ratio and our conversions as well. Okay, so balancing that reaction correctly is important. Okay, so I multiply across the whole top, divide by the whole bottom, gives me 2.5 moles of O2. Now we're going to go from moles of one substance to grams of another, okay, or from grams of one substance to moles of another. We're adding one more section to our T-chart, okay. So we're going to go from moles to grams. I'll give you the balanced equation here so we don't have to spend time with that. Okay, what mass in grams of glucose is produced when 3 moles of water reacts with carbon dioxide? Yeah, right. You know this is carbon dioxide, water, and oxygen, so that means this one has to be glucose. Right? Okay, so we want to know the mass in grams of glucose, so that's our unknown right there. Okay, and sometimes I like to put a question mark so I know what I'm looking for. Okay, or I might even put a question mark above it in the chemical reaction. That'll help me know what I'm going for. Reacts with 3 moles of water. Okay, so in our T-chart we're going to start with what we know. 3 moles of H2O. Okay, my overall goal is to end up in grams of carbon dioxide. Can I go directly from moles of water to grams of carbon dioxide? No. What do I need to go to? Moles of carbon dioxide. Good. So I'm going to go moles of water to moles of CO2. Okay, and this is called what step? The mole ratio. Good. And so what are our coefficients here, top to bottom? 1 to 1 water. Right? We have a 1 coefficient here. But what's water's coefficient? 6. You're right. You're right. I don't know why I put CO2. We want glucose, not CO2. That was my fault. Sorry. When I make mistakes, just tell me. Nicely, hopefully, but tell me. C6H12O6. Okay, so that's going to make our mole ratio different. Okay, so 1 mole of glucose to how many moles of water? 6. Okay, there we go. That's what I was looking for. Does that make more sense? Okay, good. So now I've canceled moles of water. I'm done with that. I'm left in moles of glucose. So if I want to go from moles to grams, I go moles of C6H12O6, and grams goes up top. So what needs to go in this portion of our T-chart right here? The molar mass. So we need to calculate the molar mass of glucose. Okay, and what do we get for our molar mass? Good, about 180 grams per 1 mole. Okay, so when we go back to converting between moles and grams, the moles is going to get the 1 again. Okay, the only place moles doesn't get the 1 is in that mole ratio step. Okay, so now we're done with moles of glucose. We're left in grams of glucose, which is what we want. So let's go ahead and multiply across the whole top, divide by the bottom. Okay, multiply across the whole top, divide by the whole bottom. Did we get 90 grams?
Yeah.
Yes. Okay, so this tells us when we started with 3 moles of water, and, at least that much or more moles of carbon dioxide, right? Because carbon dioxide is our other reactant, so that means we've got to have the right ratio of that too. When we don't mention our other reactant, we assume there's enough of that, or there's extra of that. Okay, does that part make sense? We're going to talk about that much more later, but we're reacting with a minimum of 3 moles of water. That should give us, if our reaction is completely perfect, it should give us 90 grams of glucose. Okay? Questions here? All right. You want to try this one on your own? Yeah? Let's try it. Anytime we see this term excess, that just means that the NH3 or the ammonia is going to run out first. Okay, so excess oxygen makes no difference in how you solve the reaction yet. We'll talk about that later in this chapter. But if you see that for now, that doesn't change how you solve it, so don't worry about it right now. Okay. Okay, you're using the same balance reaction here. Okay, but it asks me how many grams of oxygen are required to produce 0.3 moles of water. Okay, does it make a difference that we're starting with our product and we're trying to find our reactant?
Yes.
No. The math works the same. We're just working backwards. That's okay. So it makes no difference what you start with. You could be comparing the quantities of 2 products or 2 reactants, or you could go backwards. It makes absolutely no difference. Okay, you're still going to write what you know. And we know we have 0.3 moles. We're trying to find grams. Okay, I like to write above the chemical reaction because it kind of clues me in on which coefficients I should be using, what mole ratio I should be looking at, things like that.
What's different?
we get about 8 grams? Okay, perfect.